We're going to look at radioactive decay from a graphical perspective because sometimes it's helpful to have a more visual representation of what is taking place when an unstable nucleus decays to become more stable. And to begin, let's just remind ourselves of the different decay mechanisms. So with alpha decay, that emission of a helium nucleus, 2 neutrons, 2 protons, is all about the heavier nuclei being unstable because they've got too much mass. And so the way that they become more stable is by the removal of some of that mass in the form of the alpha particle, and in so doing become more stable. But it's more nuanced than that. It's about changing the neutron to proton ratio. If we look at the example of uranium-234, we've got 92 protons, but the number of neutrons is worked out by the difference between 234 and 92, isn't it? So we've got 142 neutrons, but only 92 protons. So we've got a nucleus which favors the number of neutrons, a high number of neutrons. So by removing 2 neutrons, 2 protons, proportionately, we're removing a smaller fraction of neutrons compared to protons. And so therefore, the ratio of neutrons to protons increases after alpha decay. And that ties in, doesn't it, with the 2 forces that are acting in the nucleus. That electrostatic repulsive force, which acts over the whole nucleus, and the strong attractive force, which acts over the dimensions of individual nucleons. And as we add neutrons and protons into a nucleus, the electrostatic repulsive force grows faster than the strong attractive force. So as the nucleus becomes larger, we need a greater proportion of neutrons compared to protons. And so alpha decay is all about increasing that ratio of neutrons to protons to increase stability. Beta minus decay is when a neutron turns into a proton. And so a nucleus with too many neutrons becomes more stable through beta minus decay, and conversely, beta plus decay is when a proton turns into a neutron. And so this is for nuclei with too many protons, and the way they become more stable is by the release of that beta plus particle. And finally, we've got gamma decay. This is the release of pure energy. For whatever reason, some nuclei have too much energy, they're in an excited state, and the gamma photon removes some of that energy from that nucleus. So let's have a look at this from a graphical perspective. And really, we're going to be looking at translations on a graph. And there are 2 different ways that you could plot this. You could either plot nucleon number against proton number, or you could plot the number of neutrons against protons, and that's what I'm going to do. Okay, but if you have a look at these charts online, you may see nucleon number plotted against proton number instead. Let's look at alpha decay. We're going to look at uranium-238 and how that decays into thorium plus the alpha particle. So what is happening here is there's a removal of 2 protons and 2 neutrons, a reduction of 2 neutrons and 2 protons from the nucleus. So if we plot the location of uranium-238, then we've got minus 2 neutrons, minus 2 protons. Essentially, this is a translation, isn't it? And we've got that vector at 45 degrees representing alpha decay. And that's the location of thorium-234. Okay, let's do the same then with the beta minus decay. The example that we'll have a look at here is strontium, and a neutron is turning into a proton, and we form yttrium. There's the beta minus particle, and because it's a particle, we need an anti-particle being produced in the form of that electron neutrino. So what is happening here? We've got the addition of a proton and the reduction of a neutron in the nucleus. So if we plot our strontium 38, then what is happening here? Let's just label that x-axis. We've got +1 proton, -1 neutron. So we've got a translation, also at 45 degrees, but in a different direction. And the length of that vector is half that for alpha decay because there's a change in 1 neutron and proton and not 2. Okay, beta plus. The example that we'll have a look at then is potassium, and that decays into argon. There's the positron. Because that's an antiparticle, it's the electron neutrino that we need. So we've got a reduction in the number of protons by 1 and an increase in the number of neutrons by 1. So let's plot our potassium. So there's my reduction in protons. There's my increase in neutrons. So it's a translation, opposite direction to beta minus. And again, the length of that vector is half that for alpha decay. Gamma decay, there is no translation. There is no change in the number of neutrons and protons in the nucleus. It's just the removal of energy. So we wouldn't plot that on a chart. However, let's just have a look at an example of one, and we'll meet this same example in the medical unit later. Technetium has too much energy, and so it decays through gamma emission, which is obviously pure energy. So we've got the same number of protons and neutrons, and that's why the element hasn't changed. And I'm hoping that you've clocked that every time we've looked at alpha and beta decay, the element changes. So from potassium to argon in beta plus, from strontium to yttrium in beta minus, from uranium to thorium in alpha, we get different elements being produced. But in gamma, it's the same element. It's just more stable because it's got less energy. And you'll notice there's a little m next to the nucleon number in technetium. That stands for metastable. What is happening here is there's a tiny change in mass as technetium decays, and that tiny change in mass is converted into energy, and that energy is in the form of that gamma photon. Okay, if we look at all of the nuclides that exist, and remember what a nuclide is, it is the specific combination of neutrons and protons in a nucleus, okay? If I just put a reference line of same number of neutrons and protons, okay? As we start adding in all the nuclides that exist, what we find is for the lighter elements, they do have the same number of neutrons and protons. So think about carbon, 12, 6, so you've got 6 protons, 6 neutrons. Nitrogen, 7 of each, oxygen, 8 of each. So that's what we find initially. However, as nuclei become heavier, we get this deviation in favor of neutrons. Okay, it goes back to the competition between those two forces, isn't it? Okay, we have to have more neutrons than protons because the electrostatic repulsive force between protons is growing more rapidly than the strong nuclear force. Okay, so this is what happens in reality. If we then continue to plot all of the known nuclides, we find that they kind of like occupy this region here, which I will highlight in here. So we have got what is known as a line of stability, sometimes referred to as the valley of stability. Okay, and this line here shows you all of the stable nuclei. Now, the reason that they're stable is to do with the Pauli exclusion principle, but we won't get into that here. You can look that up if you want to. Surrounding it, what we've got is a valley of, sorry, not a valley, a sea of instability. And these are all of the other nuclei that exist in the universe, and they are unstable. Okay, and the reason this graphical representation is quite a useful way of thinking about it is, imagine a steep-sided valley, okay, in geography. Okay, there is your line of stability. So that is the location of the stable nuclei. What's happening in decay is unstable nuclei are becoming more stable. In other words, they're working down the valley. They're rolling down the valley from a position of instability to a position of stability. And when we look at this from an energy perspective, a little bit later, what we're going to discuss is that stable nuclei are in a lower energy state than unstable nuclei. Okay, so if we plot all of the nucleides that exist, there's a huge, thousands of them, okay? Most of them are unstable, but we've got this line running through the middle here where we find all of those which are stable, okay? So here's what that actually looks like. And if I just return back to the vectors that we had for alpha, beta minus, and beta plus, alpha was a vector in that direction, wasn't it? -2 protons, -2 neutrons. Beta minus was a vector of half the length, -1 neutron, +1 proton. Beta plus was a vector of equal length of beta minus, but in the opposite direction. Okay, so we've got -2 neutrons, -2 protons. Here we've got -1 neutron, +1 proton, and here we've got +1 neutron, -1 proton. Okay, so on this diagram here, you've got the n equals p line. Okay, so that is what it would look like if every nucleide in the universe had the same number of neutrons and protons. We would find them on that line, but we don't. We find them on a line which favours the number of neutrons. So we've got this line of stability in black. It's a bit of a jagged line, isn't it? Running down the middle of this chart. Okay, that is the location of all of the stable nuclei. And surrounding that, above and below and beyond, okay, we've got that sea of instability. Every pixel is a nucleide which happens to be unstable. So radioactive decay is the process by which an unstable nucleus becomes more stable. And what that means in terms of this graphical representation is that we're trying to get closer to the line of stability. Okay, we're trying to get to the base of the valley where we find stability. So let's begin with alpha. They're color-coded in yellow. And as I said to you at the beginning, they tend to be the more massive nuclei. So they're located kind of here, okay, actually beyond the line of stability. They're too massive to be stable. But look at the vector for alpha. It's pointing in that direction. Every alpha decay is bringing that nucleide closer and closer to the line of stability. Beta minus decay. So they're color-coded in blue. So all of the unstable nuclei that decay through beta minus are in blue. And that vector points in that direction. So those nuclides become more stable by moving in that direction towards the line of stability. And hopefully you're getting the idea now. Beta plus, they're in orange. So they decay by increasing the number of neutrons and decreasing the number of protons. And that vector pointed in that direction. Again, we're taking those nuclides closer to that line of stability. So hopefully that's a really helpful way of visualizing what is taking place in radioactive decay. The reality is it often takes multiple decays in order for something to become more stable. So let's have a look at what we call decay chains. And I'm going to use the example of uranium-235. And it undergoes a large number of decays and eventually ends, as often is the case, in lead. And we'll look at lead specifically later on. Lead is a really stable combination of neutrons and protons. And once we reach lead, we've reached the lowest energy state and all further decay stops. Uranium decays in multiple stages. There's an alpha decay, first of all, followed by beta minus, followed by alpha, followed by beta minus, followed by alpha, so on and so on. There's more. It's coincidence. It's flick-flacking between alpha and beta. Not all of them do. Not all nuclides do. Okay, but that is what uranium-235 does. So in terms of writing this as a kind of a linear series then, we've got alpha first of all, so we must have 23190. Look that up on the periodic table. It's thorium. Then we've got a beta minus decay, no change to the nucleon number, increase the number of protons. Look that up. Element number 90 is protactinium. Then we've got an alpha decay, so that's what, 237, 89. 89 is actinium. Then we've got a beta minus decay, 227, 90, thorium. We keep going, and eventually we get to lead, and the process stops. I mean, interesting, we've got thorium in two places, but they're different isotopes, they're different combinations of nucleus, aren't they? We can deduce that thorium-227 is more stable than thorium-231 because it's further along the decay chain. Okay, now I'm just going to add in the number of neutrons just because that's going to be useful for the chart. So 235 take 92, we've got 143, 231, we've got 141, 140, 138, and 137. Okay, they're the number of neutrons. So if we now plot this, it's going to look something like this then. So here's our uranium-235, 92. First decay is alpha, so minus 2 neutrons, minus 2 protons. So there's your 231 thorium. Then it's a beta decay, so it's plus 1 proton, minus 1 neutron. So that's your protactinium. Then what have we got? Another alpha decay. So there's your actinium. Then we've got another beta decay, so minus 1 neutron, plus 1 proton. Okay, and so now we're plotting the decay chain, the decay series. Okay, and that will terminate eventually at lead. And what that means in terms of our kind of graphical representation then, okay, is uranium-235 is high up the side of the valley. It is unstable. And through a series of decays, it is working its way down the valley to that line of stability, at which point the decay stops and terminates at some element, which in this case happens to be lead. So we've had a look then at alpha and the beta decays graphically. We've had a look at how this relates to kind of stability. And finally, we've had a look at the fact that many decays are multiple events. They are decay chains, and we've had a look at how we plot those.